Hey, physics students, it's Mr. Heinrich here, and we're looking at one of the projectile motion problems that I assigned you. And after looking at this, I realized this is a pretty tough problem, and I didn't think it was until I went to do it. So let's get into it right away. If you are joining me and you're not in my class, the first thing I tell students to do with projectile motion problems is to set up their given information in the X and Y axis. Now we know if this is a golf ball that's being driven a really great distance, 301.5 meters at 25 degrees, we know it's going off the tee at a very, very fast rate. But we don't know the velocity, which is why this is a difficult problem. Normally, we have this information and we don't. So we're going to need to use a system of equations. So I'm going to consider the whole trip. I'm going to find that initial velocity, and then I will address how we actually get the max height, which I call delta y max. Now, all of that said, if we're considering the whole trip, my entire trip, I do not displace in the y-axis. Now, yes, I do climb and my height goes up, but then it starts to come down. And what is the definition of displacement? It's a change in position. If I start on the ground and I end on the ground, I did not change overall my y position. So it's zero. And delta x is actually given to me as 301.5 meters. A lot of times that's what they're asking us to find, but here they provide it for us. Now we also know that in the y-axis, we have gravity acting, which is causing our ball to consistently accelerate downward at a negative 9.8 meters per second each second, or 9.8 meters per second squared. Our acceleration in the x-axis is zero, all right? And again, if you're not sure why that is and you're joining me from someone that's not in my class, you want to ask me questions on that, you can in the comments. All right, let's keep going. So we need three pieces of information. That's what I've taught you guys. We need three pieces of information in one of these columns to find what? To find time, because time applies to both the X and the Y axis. So let's keep going. Well, we don't know VI. However, we still know that even though we're not aware of the value, VI is made up of both an X component and a Y component of velocity that we will call VIX and VIY. Now, let's say this was the number 20. Let's say it was launched at 20 meters per second. We would just put 20 times the cosine of 25 because we know we're dealing with the adjacent side, and so we use the cosine function. However, I don't know that it's 20, so I have to generically write VI times the cosine. And you could say theta here if you wanted to stay generic, but I'm going to kind of do a hybrid of both. So I'll have VI cosine 25. And here, since we're in the opposite side, we're doing VI times the sine of 25, right? So in these givens, I'm going to say that VIX is kind of known. Half of the expression at least is known, cosine of 25 times some unknown initial velocity. And VIY, the Y component, is that hypotenuse times the sine of 25. And this is why we need a system of equations. We need to simultaneously, with two unknowns in both equations, the same two unknowns, construct the equations and then either do substitution, elimination, or a new method that I'm going to show you. Okay. It's basically substitution. All right, here we go. Delta x, this is our second kinematic equation that you learned, written for the x-axis, and we know that since there's no acceleration in the x-axis, gravity does not act in the x-axis, that this is zero. Zero times anything times that half or times that t squared is zero. So we get the simplified expression that delta x equals, now I'm going to not write VIX, I'm going to write VI cosine 25 times time. Don't forget that part. And then I'm going to also express this equation in the y-axis And if I'm going to simplify this one, this is 0. We said so. For the whole trip, it's 0. And so we get to say 0 equals, what's VIY? It's VI times the sine of 25 times t plus 1/2 AYT squared. Now, math teachers would do what here? They would take a t and they'd factor it out to the front. And they'd have two things equaling 0. T would equal 0, and then whatever was left in the parentheses would be equal to 0. While that is technically the correct way to do it, I like to shortcut it like this. Just divide everything by t, because 0 divided by t is 0. This t cancels with that 0. Excuse me, this t cancels with that t. We have 0 equals VI sine 25. I also, as you guys know, like to say half of negative 9.8 is just negative 4.9. So I'm plugging that in right now. I'm not putting units in because it gets really cumbersome to write. So again, we're doing this hybrid of some given information and some generics where we're not actually plugging in values. For instance, I could plug in the X, but I'm not going to do it just yet. All right. Let's simplify this a little more. Oh, you caught it, I'm sure. What happens with that t and that one? That goes away. So this is just negative 4.9 t. All right. Good. Now I'm going to add the 4.9 to the other side, t, add the 4.9 t to the other side, and that would equal VI sine 25. Let's call this equation 2, and let's call this one up here equation 1. And what you could do is you could solve this equation for VI and plug it into here, and there's nothing wrong with that. It's a good way to go. But I've found over the years, you could actually just take this equation and divide it by that equation. You can do that. Yeah, you can do that. Notice there's only two terms. And if you just got 1 and 2 terms on either side of the equal sign, and the same thing with the other equation, you can just divide the two of them. So what do I have here? I have VI's canceling out, and I have sine of 25 over cosine 25t. So let's do something real quick. I know some of you know what I'm going to say next, but let's multiply both sides by t real fast. Okay, so this t and that t would cancel out. And I'm going to re-express this as t times 4.9t would be 4.9t squared divided by delta x equals, that's right, the sine of 25 over the cosine of 25 is actually the tangent of 25. Let's rearrange a couple more things. Man, this is a long problem. And it kind of makes sense. They gave us very little to go on, so we're having to really flex our algebra muscles here. All right. So I multiplied by the reciprocal, right? So this delta x goes away with this one, 4.9 cancels out, and we brought it over here as well. So we'd have t, let's say squared is equal to, what's delta x? Well, let's plug it in a second, but let's finally just write this. Right? Okay. Now I'm going to take the square root of both sides. So t will equal the square root of, now we'll plug in our information. 301.5 meters times the tangent of 25 all over 4.9 meters per second squared. So don't forget that this was negative 9.8, right? And so it still retained the unit of meters per second squared that we had up here, which makes sense because look what happens to your meters. Your meters cancel out. What happens? You multiply your second squared to the top if you're doing your unit analysis. These second squareds cancel out, and you're left with the square root of second squared. Gives us seconds. We know we did everything correctly. It's important that you can track your units. Otherwise, you're not sure if you might have made a silly mistake, like I almost made over here. Okay, let's put this in the calculator. Maybe you need help doing this. So I'm going to put in my square root. I'm going to get 301.5 times the tangent 25 divided by 4.9, close parentheses for the square root. And I get 5.3, let's round that up to 6, 5.36 seconds. Whew, that was a lot of work to not even find the thing they're asking us to find. Now, I already know we're going to need to know this VI in order to get that Y max. So let's just use, it doesn't matter which equation we use, equation 1 or 2, we can use this time we just found to find the VI, okay? So I'm going to actually use equation 1. Why not? We can. So I'll go ahead and say re-expressing is delta x equals VI cosine 25t, right? So let's solve this whole thing for VI. So I would divide both sides by, catch this, I would divide both sides by cosine of 25 times t, right? And that would equal my VI. That would be my VI. So just remember, don't accidentally put that t, this t inside the argument for cosine. It's just the cosine of 25 times t. Now on my calculator, to save us a little time, I'm just going to put in the values 301.5 divided by, I'm going to open parentheses so I don't make a mistake on my calculator. And I have the cosine. In fact, I'm going to put the time first, 5.36. It doesn't matter what order you multiply things in, right? You still get the same result. And then the second parenthesis for the denominator. And you'll see what I did. I'll just kind of scroll back, right? And then I'm going to hit equals. And look at that. We have 62.07. You might say, just call it 62. Okay. I don't really push significant figures in physics as much as I do in chemistry. So here we go. We've got our VI. Now, I'm going to use this space right here. Whenever I'm looking for Y max, remember there's always more than one way to do something, but this is the equation I like to use. I like to use VF equals VI. Oh, VF squared equals VI squared plus 2A delta, and I'm going to say Y in this case, right? But we can't just be general. We have to be specific for Y or X. So I better say VF Y squared, VI Y squared plus 2AY delta Y. Now check it out. I'm going to say max. You might say, well, that seems arbitrary. You could just do that. Well, you can as long as you put the right parameters in for this stuff. You need to realize, and the hint was in the problem in the book. I didn't write it up here, but the hint actually says to us, it says at the top of its flight, the ball's vertical velocity is 0, right? So we know at the top, we know this x velocity never changes. It never stinking changes. Always is the same amount because there's no acceleration in the x. But we know the y velocity is constantly slowing down. And finally, at the very top, the final y velocity for a moment is 0 meters per second. So keeping that in mind, when we are at y max, my final velocity in the y-axis at that moment is 0. So I'm going to call that 0, right? I'm going to take this and subtract it to the other side, okay? So I'm going to say minus VI squared, VIY squared equals 2AY delta Y max. Let's divide both sides by 2AY. Let's finish this sucker off. Okay, I'm going to flip the equation around. Delta Y max is, let's plug in our values. Now we know VIY is this right here. So I'll say VI sine 25. That squared. Now notice we're not squaring this negative. That came from us subtracting this term over, right? So it's just VIY that's being squared divided by 2 times negative 9.8 meters per, oh, look at that. Look at me go. So I started plugging in some values, but not others. Let's just go ahead, so I don't have to rewrite all this. What's our VI again? What's our VI again? 62.07. So right in here, you're going to want to put 62.07, right? Right in for that VI. So on my calculator, I'm going to put in, you'll notice your negatives, you can just disregard those. They divide out, right? So don't bother putting those in the calculator. It's extra work for no good reason. I am going to put in, though, parentheses 62.07 times the sine of 25, close parentheses. Notice I close the parentheses for the sine of 25, and I close these parentheses because I want to make sure I square the whole thing, right? I don't want to mess up and accidentally just square the sine of 25. And I'm going to say divided by. Now, also, you should get used to this. 2 times 9.8 is just 19.6 divided by 19.6. And look at that. We have a max height reached of 35.1. Yeah, I guess we'll stick with those 100th place rounds. It's the 35.11 meters. Delta Y max is 35.11 meters. Oh my goodness, we are done with this problem. So you better all have it when I see you next time. All right. For those of you who aren't in my class, I hope this helped you out. And if you have any questions on other questions, feel free to reach out. All right. Have a great day.